Thank you, Isabel. Good morning, everyone. My name is Dan Pitt, and I'm really pleased to be here with you, and I'm really thrilled to see a full room of people interested in this subject. We're hosting this second Open Networking Summit in cooperation with Open Networking Summits, Guru and Asena. And I think it's just a great opportunity to kind of bring everyone up to the same level of understanding of what this is all about. So in my half an hour or so this morning, I want to share with you what we think SDN really means, where OpenFlow fits in. They're not the same. They're not identical. And then what the Open Networking Foundation is doing. And I hope that you will get sort of a better appreciation of why this is really important. My title slide here says, a revolution in networking, but the second thought is it really more of a revelation in networking? And we're going to get, here and there into some, bits and bytes and how things actually work and the mechanisms. And you want to know that. But more importantly, I think we're into a new way of understanding networking and thinking about networking. And I think it's a pretty fundamental change. I've been in networking really my whole career. And this is probably the most important change I've seen in about 25 years. I spent, as Isabel said, 5 years full-time in academia. I've spent some part-time before that, and I did some startups. I got away from networking for almost 10 years. And it took Nick McEwen and Scott Schenker about 6 months to drag me back into it. I got sort of tired of it in the, after the bubble burst and all that, and it had become a little bit derivative and repetitive, and it was just kind of a hodgepodge. And I didn't really understand why that was until I got to talking to Scott Schenker, and he started talking about fundamental abstractions. And I realized this really is what networking has been waiting for a long time. So I hope that by the end of the session today, we'll all have at least a basic understanding of what SDN and OpenFlow are, who we are, and really what the state of the art is in this amazing community. And I think I will not be the first person to use this word community that you'll hear this week. That's something that's also different about this movement almost. It's not just about a protocol. It's not just about a technology. It really is a movement that the whole industry is causing to happen. And we're part of this community. And this meeting, of course, this week is really the world's foremost meeting of the SDN community. So software-defined networking, here's what it does, and then I'll tell you what it is. The world we've inherited, and for good reason, is one of networks that are mostly static. They're inflexible in ways that I'm sure those of you who come from the service provider realm will understand. And for those of you that come from the enterprise realm, I'm sure you'll understand the frustrations of getting the network to serve precise business interests. What we're moving to is programmable networks. And it's interesting to consider the origins of SDN and OpenFlow in programmability. I'll explain that in a second. And the goal of programming networks is not for its own sake, but it's really to make the network serve business ends. So where did this come from? At the summit, you'll see Nick McEwen, and you'll see Martin Casado. Martin got his PhD with Nick. And it was Nick's frustration as a researcher and Martin's frustration as a programmer with networking that led to the development and invention, really, of software-defined networking. From Nick's viewpoint, he said, I want to do research in networking, but it's hard to really do research because I can't experiment with anything like a new protocol. What if I wanted to try something beyond IP? And what comes after IP? JP, KP, who knows? But there's no way to experiment with it other than simulation. You could build one box. You could maybe design one chip. But you can't build 1,000. And if you do it in software, you're not simulating the real internet. So there was just no way to continue to do meaningful research in networking. People were starting to leave the field. Martin's viewpoint was that as a person who grew up programming everything, you programmed it. If you didn't like the way it worked, you changed some lines of code and you ran it again. and you could iterate as fast as you could write code. Well, with networking, that wasn't even possible. You could not program the network. It was done by autonomous, self-contained boxes that had complete view of the network. They understood, they learned what the topology was and the state, distributed state. This is something that originated in the Cold War when the funding for the internet came from the Department of Defense. And they said, we want a network that can withstand a nuclear attack. If you take out a couple of nodes, it doesn't destroy the network because each box is autonomous. No central point of failure. Well, that lasted 30 years, but it doesn't really hold up any longer. And because these networks had these independent autonomous boxes that exchanged these complex protocols, there was no way you could actually program something directly. You had to institute it in some kind of a protocol. They all had to agree on things, and it was very indirect. So software-defined networking, in my view, is the ability to directly program network operation using ordinary languages, ordinary operating systems, ordinary computers, and ordinary programmers. So if you're involved in building or operating or using networks, this is going to affect you. And I think that we're looking at this now saying, gosh, this is really kind of different. And I think 5 years from now, 10 years from now, we're going to look back and say, how did we live so long without being able to program our own networks? It's so easy to do, and it's so obvious. Some of the particular technology trends have actually made this the right time for software-defined networking. We've had two important advances. One is in hardware and ASICs and in CPUs. The other is in software engineering and distributed computing. And these things together have made it possible now to do what we are doing with SDN. We are seeing now this trend away from hardware and appliances to open software. And this has so many manifestations. I spent some time with an Australian company that was working on fiber optic impairment monitoring, long distance connections, fiber links. The way it's done today, you cart in an appliance, a $100,000 appliance. You take all the traffic off the network. That takes 3 months of planning at AT&T. And then you run some tests, and then you gradually get the traffic back on, and you go and you run some other tests. They're replacing that with a passive optical tap. It just looks at the light coming off the fiber, and using software and a variety of downloaded microcode modules can do any number of impairments in real time without taking traffic off. So the power is now in the hands of those writing software. With networking, you're going to see that what had been, for example, an appliance for load balancing or firewalls can now just be a software module written to some standard nice API in the part of the network software that we call the network operating system. So the value is moving, I think, in two directions. It's moving to ASICs on the one hand, and it's moving into software on the other. I mentioned we had this distributed control plane, where the control functions of where you route traffic resides in every box in the network. And as we've had more and more requirements and more diversity of networks, we've had more and more protocols to handle all of these needs. Does anybody know how many RFCs there are now out of the IETF? Anybody want to guess? 6,000. It's almost exactly 6,000. So these autonomous boxes that run this distributed control plane have tens of millions of lines of code to implement all of these protocols. And each one is designed for a particular use, and it's been added to all the others in what's been called a bucket of protocols. Sometimes some of the protocols undo what the other ones do, because now we have to find a way of doing it differently. So it's what I call them point band-aids. When we go to a logically centralized control plane, and I say logically because with distributed computing, it doesn't mean it's in one box, it's a single point of failure. You can now have a global view of the network. You can program it once instead of having to program it in every box. And the control plane now has two advantages. One, it can control all of the network elements at once. And number two, looking upward, it can be programmed directly by all of the requirements of the business that owns and operates that network. We've also seen this trend from custom ASICs and FPGAs into merchant silicon. Now, many of the big networking vendors have relied on their custom ASICs for their competitive differentiation and to do, in an efficient way, all of these different functions that you need in these RFCs. These companies, even themselves, are adopting merchant silicon. And this is certainly happening first and fastest in the world where it's all Ethernet. But it is really spreading to just about anywhere that you can have network forwarding. And we're going to take great advantage of merchant silicon in this world we're coming to. And finally, and this is sort of subtle, a move from protocols to APIs. When you have this distributed control plane, and you want to get something done, you have to have a protocol that goes between one box and another so they can mutually understand what they are doing. And these protocols are standardized by a committee and then implemented in proprietary operating systems. It's a slow process and an imperfect process. And in particular, when you're trying to make something happen in the network with these distributed protocols, you have either the law of unintended consequences or the whack-a-mole problem. You contort it to get to do what you want it to do, and it does it, but you discover some unexpected problem pops up somewhere else. So then you go and you whack that one down to fix that, and something else pops up. That's because of the indirect nature of distributed protocols and their sort of non-programming. Well, when you go to APIs, you program these things directly. This also says that where the power in the network resides is now up above the APIs, where you can take elements of policy, security, and traffic engineering and use them to directly determine what the network does. It also intimates that networking is changing into a software discipline. And in that sense, the even larger implication is that networking is becoming part of computing and not going to be so separate from it. So Scott Shenker talks about the lack of fundamental abstractions in networking, and he puts them in these three categories. We have now a forwarding abstraction, and it's OpenFlow that really implements it. This is a common API for programming the network hardware. This is the interface that we've created inside the forwarding elements, inside the networking boxes, that allow this software control to talk directly to the forwarding plane. So that's an abstraction, and we've done a lot of work on that in the Open Networking Foundation. We're doing some more, and perhaps even some more fundamental work on that. The state distribution abstraction, where you had distributed state. Each of the networking nodes had to kind of exchange state information. It took a while to settle and stabilize when it did. Well, now we have a single state distribution algorithm. If you look at the OSPF standard for open shortest path first routing, the Dijkstra algorithm is the heart and soul of that. In the 300-page spec, about 5 pages are Dijkstra, and about 295 are for how do we manage this distributed state. Well, now you can calculate your routes very directly in a single place in your software control. And the other abstraction is global management. This is now above this API. The network has a logical appearance, and it can be managed as essentially one switch rather than individual ones that have to be programmed one at a time. So these are three abstractions that we really try to keep in mind as we're developing the elements of software-defined networking, including what we standardize and what we do not. Tomorrow I'm giving a talk called SDN Standards, What and What Not. And we'll talk about the what and the what not that we're doing. I'll give just a few words about it here today. I want to show this just to give us kind of a picture context. You're going to hear a lot today from the other speakers about how these concepts are used and applied in a variety of scenarios. But let me just spend a moment giving you a picture of sort of what it looks like. So we have here these three tiers, and we have switches now, whether they're hardware or virtual software switches. We have control plane software that really replaces all of the extensive thousands of RFC processing in the switches. And then we have the applications above that. And each of these represents sort of one of those fundamental abstractions. We have the forwarding abstraction, we have the distributed state abstraction, and we have the global management abstraction on the top. So the applications up there, and it's very imprecise here. I haven't said whether these are, business applications, like payroll, or whether they're network applications. It almost doesn't matter. This is where how you want to use the network for business purposes comes into play. All they see is a logical virtual view of the network. It can do these things for me. The control plane software figures out how to translate those requirements into commands to the switches on how to route traffic. It's as simple as that. The OpenFlow protocol conveys that information to the switches, and all they do is process the traffic as it comes through. So we are assuming that these switches receive frames of information. They can delineate the beginning of a frame and the end, and they can count a certain number of offsets. So they have flow tables. I'll show one of those. Just some examples of what lives in each of these tiers here. But this is kind of the picture. Now, I don't mean to imply that any of these things are boxes, physical boxes. These are, for the most part, except the V ones don't have to be. The others typically are. The control software, that can be in a server, can be in sort of distributed servers. The applications can be software modules residing locally. They can be program calls. Any number of choices in how you do those. So this does not imply implementation. This is architecture. Now, OpenFlow is a part of software-defined networking that does this. Once the controller knows, the control software knows what it wants the network to do physically in terms of routing flows, it has to convey that to either the software switch or the hardware switch. And this is a place where a protocol belongs, and it's also a place where a standard belongs, because you've got many people making control software, many people making hardware software switches. You want them to interoperate with each other. So here's where we do need a protocol. And it's my view that without this separation physically of the control plane from the forwarding plane, you don't have the global management abstraction, and you don't have the distributed state abstraction. You might have the forwarding plane abstraction, but it's essential to have these separated. When you do, you need a protocol to communicate this information. OpenFlow is the standard way of doing that protocol. There are some proprietary ones that are out there. Mostly they predate OpenFlow. Let's see what it looks like. Here you have in a switch a client, an OpenFlow client, that receives this protocol, translate it into stuff that runs in the hardware. I heard somebody say once that the cost of having an OpenFlow client and a switch is really pretty low. And the cost of not having it there can be extremely high. This is a flow table that resides in a switch. And this one actually shows a number of header fields that could be in an Ethernet frame carrying an IP packet. MAC source and destination addresses, IP source and destination addresses, destination ports for TCP, and then actions and some counts because we have counters. Basically what this says is, if you receive a command from the switch, from the control software that says, load these things into your table, and then you get a packet that comes in, you look to see what that packet looks like. And if it looks like this, then you take this action. You forward it out of port 1. You don't have to know, what that means in terms of distributed state. You just know that's what you're supposed to do. Now, with merchant silicon, it's mass market, it's low cost, but it's also pretty protocol specific. it looks for these particular fields. Does that help you get away from IP and Ethernet? It does not. But if you have an ASIC or an FPGA or a network processor, you can look anywhere, or even in software, you can look anywhere in an entire packet, find the bits you're looking for, the patterns. If they match something in your flow table, you simply take this action, forward it out of this port, out of multiple ports if it's multicast, drop it, send it to the controller, or whatever. When we get to where we don't care what those fields mean, then we can go beyond IP. Look at this byte offset into these bits. If you see this pattern, take this action. The switches don't need to know what they mean. They don't need to know they're talking IPv4, v6, or HP or JP or KP or whatever the protocol might be. They can also look deep into the packet in layers 4 through 7. We have a number of member companies that are doing that, and take into account upper layer influence in what happens to that packet after it comes in. Now, I mentioned multicast. We've had multicast in networking devices for I think 16 or 17 years. Does anybody use it? Hardly anyone. It's almost impossible to use, to set up multicast trees and configurations. Multicast is trivial with this. You just tell these switches, when you get this packet in, send it out these ports, multiple ports, and you can figure that out in the control software very easily, and you just tell the switches to do that. It's direct programming. You're going to hear a lot of examples today of where this applies. And I'm just showing this to give you an idea of the diversity of requirements that this approach to networking solves. This is a philosophically different approach to networking, where now, because you can program it, you can make it really do what your particular needs require it to do. So we have examples of all of these companies, of course, in ONF, but mobile operators, fixed line carriers, many enterprises. Now, the hyperscale data centers are sort of leading the charge because their massive scale requirements make this kind of a no-brainer. But their purposes are a little different from the others. Some of the purposes you'll hear today are to dramatically lower the cost of building a data center. Other purposes are to facilitate business process improvement in enterprises. I really want to run my business better, and I got to get the network to help me do that and not be an obstacle. Carriers have kind of a couple of different viewpoints. One is we've got to do something on our equipment costs because they're not going down as fast as our traffic is going up. Others say, I want to compete with the data center operators and the cloud providers. Others say, I just want greater service velocity. I want to be able to create my own services and not say to my vendors, I need this feature. They say, OK, well, we'll go to some standards body. It'll take 2 years. And then we'll have to program it into our proprietary operating system and get it to work with our NICs. And then we'll deliver it. And maybe it's what you want 3 years later. They want to offer some new service. They want to be able to hire their own programmers or their own contractors or their own whatever it is, program it themselves, introduce it in 6 weeks. This is going to lead to a very interesting competitive marketplace for this software enhancements. I think for small and medium enterprises, public clouds are going to become more and more attractive because they will be more and more trustworthy. Larger enterprises will start with private clouds and experiment with public clouds. What they like about this is that they can view their virtual network in the shared infrastructure and feel like they can control it themselves. The interfaces that I showed in these application areas, from carriers or cloud operators to enterprises, give the enterprises a logical view of the network that seems like it's their own, and they can get it to do what they want, but they have economies of scale from the cloud providers. They don't worry about managing the plumbing any longer. Financial services, I've talked to some of these companies, and requirements that you don't always think of. If you have government compliance mandates, for example, to separate what you do with your money from what you do with your client's money, what you do in commercial banking versus investment banking. Some of these firms have had to run multiple separate infrastructures. And redundant, poorly utilized, duplicate management. They're now thinking, I can build one infrastructure. I'll have logically separate overlays, and they'll be auditable. So if the SEC or some other government body says, prove to me that you're not cross-subsidizing, I can do that. They're very excited about this. Other kinds of mandates, government mandates to keep traffic inside the boundaries of your country. Certain data cannot leave the country. That's easily affected here. Affected with an E. So, a few words about the Open Networking Foundation. We are 1 year since our public launch. And I have two slides, one on commercialization, one on standardization. We're not just a standards development organization. We exist to promote the commercialization and success of software-defined networking. And we will standardize the things that need to be standardized. We're not just here to count how many standards we produce. So we want to make SDN the new norm for networks, ubiquitous, not even a second thought. And our mission is really commercial, to create and foster this market. I'm trying to figure out, I'm coming up for my annual review and have goals for the next year. How do I measure that? It's not trivial, but it's not impossible. We are very much user-driven. These are the companies that are on our board. You notice there are no vendors on our board. We have lots of vendors as members, but they're not allowed on the board because the users are driving this bus. We have now 66 member companies. It's growing almost every week. So the board has unique power in that it charters the working groups and approves the standards and the work plans. It also appoints the chairs of the working groups. Now, these come from vendors as well as from users on the board and not on the board. But they're beholden to the board for their marching orders, and they have to apply and be selected and approved by the board. We have standards being developed by implementers, people close to the commercial result who have a financial stake and a commercial stake in the decisions that they make in the standard. So we don't have a lot of theorists. We don't have a lot of researchers. We work with them in other capacities, but this is a real-world standard that we do. We also are keeping in mind that as we move to the world of software, a lot of standards, if they become standards, are developed by the marketplace itself, not in a closed room by a committee. In the networking world, it's always been, oh, here's a new need, we'll need a new committee and a new standard. Not so much in the world of software. So we're going to standardize as little as necessary to make this market successful. We're located in Palo Alto. We try to operate like a startup here. We try to be lean. We try to be agile. We're fast. We're not beholden to too many historical processes. We build them as we need them. And we try to understand the needs of our customers and act to satisfy those. So we do some standards. We're standardizing the OpenFlow protocol because it needs to be standardized. But we're also studying a lot the architecture and the frameworks for these software constructs that live really above the OpenFlow protocol. We want to understand what those interfaces and APIs should look like, how you characterize the network. There are multiple instantiations of these today. We want to know why they're different. We're not going to standardize them unless we feel there's an industry need for us to do so. But we are going to be where people understand what they mean and why they're there. Isabel Geese is chair of our Market Education Committee. Market education is why we're here today. It's an exciting concept, but we want to make sure people understand what it is and what it isn't. So we're just done producing a white paper, which we'll have on the web soon, maybe even this week. And we're trying to make people understand how software-defined networking concepts can really work for them. It's so easy to customize it for your use, as we've seen in these industry examples and you hear later today. And I mentioned community earlier. Well, when we get together in this Market Education Committee, It's almost like being in these open networking summits. There's this feeling of, this is a movement that's good for all of us. It's not about me, it's about us. And that's the feeling we have. A little bit something different about us. We have intellectual property rights agreement with our members. It's different from a lot of other standards organizations in that it's not just reasonable and non-discriminatory terms that you need to agree to license your intellectual property to other members with. It's royalty-free. So there's no argument about what's reasonable and what's non-discriminatory. Earlier in my career, I was with a big company, and they thought that their licensing terms were quite reasonable. Startup company said, that is so reasonable, it'll put me out of business. So we don't have those arguments. We don't spend time with lawyers. We move quickly. You'll see most of our board of directors here this week, the 7 companies and the 2 professors representing themselves who started it. These are the members we currently have in our organization. This is remarkable for its diversity. Certainly we have the networking vendors, but we look at all the chip companies and network processor companies we have. Look at the software companies, large and small. Certainly we have VMware and Citrix, but we also have Infoblox. We have companies like IP Infusion. We have line rate systems. We have tiny companies like Plexi, and we have huge companies. We have computer companies, Dell, IBM, HP, Oracle. I spent a lot of time in my career doing networking computer companies, and I finally left because they weren't interested in networking. It wasn't important to computing. Now, it could hardly be more important than it is. I asked one of them recently, how important is networking to your computing strategy? Dan, I cannot overestimate for you the importance of networking to our computing strategy. And indeed, as networking becomes a part of computing, you're going to find these companies selling really suites of products and tools and management software to enable people to manage and virtualize their network and their computing and their servers and their applications and even their storage from a common viewpoint with a common suite of tools. We have users here. We have carriers from Europe and Asia and North America. We have companies, in Asia, all over Europe, the Middle East, North America. We don't have any members from South America or Africa yet, but we do have people who live in these geographies who work for our member companies. I'm not going to go through this in detail. Slides will be, I believe they'll be posted. And I'll have this slide tomorrow, so it'll be posted in that slide set as well. So we have organized ourselves into a variety of technical activities and marketing activities. Some are chartered official working groups. Some are not at that stage yet, but they're very intense discussions. We have large numbers of participants in this organization. And I'm on the mailing list for all of these things. And I am amazed at not just the quantity, but the quality of the contributions that we are getting. And I read some of these postings and some of these proposals, and it just makes my brain hurt because these are really deeply thought out and fascinating to read. And a lot of those people are going to be here this week, and some of them are in the room right now. OpenFlow is what we are standardizing, and it's a foundation that everything else is built on. So we have focused on that for the time being. We inherited OpenFlow 1.0 and 1.1 from Stanford, and then the predecessors to that. And we, since then, have produced OpenFlow 1.2, which added IPv6, an extensible expression which really improve our growth in the future. We created OpenFlow configuration protocol with a schema and a protocol. We issued 1.0 earlier this year. 1.1 should be coming up to the board at our board meeting later this week. OpenFlow 1.3.0, I think we're going to call it. We'll find out at the board meeting on Thursday. Some additional features. And we're thinking that this is probably going to be a good stable point for everyone to try to build to. We've just had a lot of requests to fix this, or can we get this in? And we've done that as quickly as we could. And we're working on OpenFlow test. Our first spec for that should be coming out sometime this summer, we anticipate. It's very important for commercialization to make sure this stuff interoperates. So we have a committee that works on conformance testing, interoperability testing, and performance benchmarking. We're working with, talking to a number of labs around the world to do these tests. We don't intend to do them ourselves. We don't intend to sole source them ourselves. We want there to be an open market in testing as well. So our focus for this year, my marching orders from the board, we're going to continue to advance the technology, get the industry to where we're getting implementation and deployment and rapid feedback so we understand it and we can make it right. We're doing everything we can to implement it. We've had our first Plug Fest. We got a variety of demos and trade show showcases that are coming up, and we've already had. And we're working closely to understand what these tests tell us about our protocol and the technology we're developing. So we have a rapid feedback loop. And then, of course, we're evangelizing software-defined networking as a concept and OpenFlow as a vehicle for attaining that concept. So what does this tell us about the future of networking? For one thing, it's going to become a part of computing, and I say yet another part of computing, which has a sort of tone of resignation. Oh, okay, just another part of computing. And I think that's exactly what's going to happen. Oh yeah, networking, it won't be the headache it's been for a long time. You don't have to take applications and configure particular addresses and ports in the application. Then you want to move something, you got to reconfigure everything by hand. No, it'll be just like you do computing. Enterprises will, I think, relish the opportunity to exit the plumbing business. They won't have to have so many people employed doing something that's not their core competence. Network operators, the astute ones, will see the opportunities in the software. We're going to write that ourselves. I think operators have a choice. Either we bulk up on software skills, or we become bit pipes, let somebody else do the high-value software. The IT department, finally, some identifiable business value, not just an unfortunate cost center. Show me what you can do to add to my bottom line, not just deplete it a little less. And finally, I think we're going to see some new startups. It's been a while since we saw a lot of new networking startups, but no longer do they require, $80 to $160 million for another chip or a switch fabric. They're going to be two guys and a dog in a garage doing software. You know what the dog is for? That's the HR department. They can't offer a BMW. They can't offer, health insurance. They can hardly even offer salary, but they can offer love. SDN is a fundamentally new way of thinking about networking. It's going to change the skills we use in networking. It's going to change its effectiveness in business. We've already seen industry take up an investment of people, product announcements, service announcements. We're going to see more this week. This is something that's actually happening. It's not fantasy. The Open Networking Foundation, we're under a lot of pressure to make this happen the right way. I'm thrilled to have this pressure. It means there's a demand for what we're doing, and we're going to continue to do it the best way we can. Appreciate your attention this morning, and I'll take a few questions.
You showed the three-tier architecture.
Yes.
The applications, the SDN control plane, and then the switches, the physical devices. I'm still confused. Obviously, there's a protocol between the controller and the switches.
Correct.
That's OpenFlow protocol. Now, for applications that's going to be sitting above the controller, will they be separate from the controller? Is the controller just implementing the server protocol portion of the OpenFlow? Does this make sense?
Yes. So this is a really great question because the answer is nobody knows. And there will probably be not a single answer. There'll be multiple answers. We don't even know, for example, we have a work group called the Northbound API, which deals with the SDN abstractions. We don't know where that northbound edge is. What is embedded inside a controller? I try to use control software rather than controller because it sounds like a box. It's control software. What is essentially part of it? What is not? I don't know. I mean, look at Big Switch. They do sort of a controller, but they open up Floodlight as an open source control software. Certainly you have to have something that translates these things into the flow instructions. But where does topology learning, where is the routing algorithm, where does traffic engineering come in? It can be embedded in, it can be a module on top, it can be along the side. We don't even know how to draw it. But because it's software, it'll be easy to experiment with lots of alternatives. That's why we want to understand what these interfaces look like and how you convey the requirements of the network to these applications. But we're not rushing to say it has to be this API, because if we did that, we would get it wrong. So I think there is just fertile ground for understanding the best way to do this. In software, there are lots of ways for software to talk to software. So I expect we'll see some XML versions, some open source ideas out there. And I think in the next 12 months, you'll see a lot happening in the software world there.
One more question. Do you see where, for network devices such as switches, where a vendor's network management, their control center, do you see that communicating directly with SDN control plane controller and or the applications on top? Or do you see the controller going directly to the network device, or it doesn't matter?
So the integration with management systems is a really important thing to consider. We talk about sort of control points and configuration points, and that's management. And there will be some ways of uniformly managing a series of switches. But vendors have their own management software, and this can be a competitive advantage. Look at operators, network operators. They have their whole OA&M systems, as well as their OSS and BSS systems. They want to interface to that, or even integrate with it, so that they can apply sort of the tools that they have that their customers are used to with a network that operates like this. I don't think that's going to be hard. It's just going to be diverse. Christos.
Yeah, so my question is, what do you see as the biggest challenge with respect to SDN? Or let me paraphrase it. What if different vendors come out with different versions of SDN or OpenFlow? Would that be a challenge, or is there any risk of that happening in the future?
Well, so OpenFlow itself is a standard, and people either will follow the standard or they won't. And the market usually says what it feels about standards. If they're valuable, the market demands them. If they're not valuable, the market ignores them. So there will be competitive differentiation, but I think in the world of open software, there's an opportunity for a lot of competition to do things that the market demands. And so the degree to which proprietary solutions add value or silo things, will be, I think, reacted to by the market.
Hi, Dan. My name is Dominique Jodoin. I'm from OpenFlow, one of those new startups that you mentioned before.
Welcome.
Based in Montreal. And
yes, we've corresponded.
Yeah, that's right. And it was more of a question or recommendation is that if you have a view of even the annual fee for small companies like us, it's still fairly high. Mm-hmm. And I would say if you want to encourage companies like us to join, I think there'll be many. I think something for you guys to consider.
I understand. And we've thought about, it's $30,000 a year to be a member of ONF. We've attracted some very small companies as well as large. We think it's kind of a high bar, but it does bring in the seriously committed. And almost if you look at the IPR agreement, if you got into any kind of a dispute about patent rights, you would blow that in a week in a law firm. So I hear what you're saying, Dominique. We don't have any plans to change it at this point. But we understand that if you're not ready to ante that up now, then that's a business decision you have to make.
Thanks very much. We'll cut the fees of the lawyer a bit more.
Okay.
Thank you, Dan.
Look forward to talking with you, Dominique. Well, thank you very much, ladies and gentlemen.
Please.